Record. Great. Okay, so welcome everyone to day two of the Quantum School. Today, we will walk you through, or Danny will in particular, in an introduction to quantum algorithms. So yesterday we saw the very basics and foundations of quantum computing. So you know what a qubit is, what two qubits together can do. And now we will see like what is this useful for. And we will go through some quantum algorithms that are very textbook, let's say, and some other that are actually more in this present era of research. So that's a bit the plan today.
All right. And so with that, we can get started. So welcome back, everyone. It's exciting to have you all back here for Quantum School Day 2. And we're going to be talking about quantum algorithms today, as Nadia said. So why don't we get started? We should probably get started with what an algorithm is. So an algorithm is a sequence of steps to solve a problem. Now, what's a problem? We want to be careful about what we're saying here. So, for example, one problem is sort a list of n numbers. I didn't tell you what the numbers were. I didn't tell you how many numbers there are. But the problem in general is to sort a list of numbers. And you can imagine going through and figuring out a way that you could sort numbers in general. That's different from an instance of a problem. And an instance of a problem is to sort this list of numbers. So here's a list of numbers, 18, 42, -6, 25, so on and so forth. And you could imagine doing something that to solve an instance of a problem that doesn't work for every instance of the problem. So for example, if I gave you the numbers 1, 2, 3, 4, 5, that is already sorted. So you could say, oh, great, I can solve this problem by doing nothing. But obviously, if I give you a random list of numbers, that's not going to work. So an algorithm is a sequence of steps to solve a problem, but ideally an algorithm should always solve the problem correctly, no matter what instance you put in. So my silly algorithm of do nothing doesn't work for the instance that we have here. We would have to do something different. And yesterday, Stefan introduced you to a couple of different ways of sorting lists of numbers, some with an ordinary computer and some with a spaghetti computer, or Bucatini computer, as it were. And those methods of sorting are algorithms that solve the problem of sorting a list of n numbers. So what happens in an algorithm in general? Generally speaking, in classical computing, there's 3 steps. The first step is to prepare an input. You put in some set of ones and zeros, and then you do something. This is some set of logic where you do some sequence of steps that turns the input into the problem solution, whatever that might be. So maybe the input is your list of numbers, the logic sorts them, and then you measure some output where you just get a different list of ones and zeros that tells you about the output. So somehow we start with an input, we do some sequence of steps where, maybe it's if this number is bigger than that number, we do something. If something else happens, we do something else. But in the end, we end up with an outcome, and we can just read it out. Oh, sorry, that was out of order. Quantum algorithms are different. And this is this slide is essentially a summary of what we want to understand today. When we prepare the state that we're putting into a quantum algorithm, we want to do something special. We want to use superposition, or so-called quantum parallelism, which we'll describe a little bit later, to do something kind of like processing all possible solutions at once. And this is a very powerful technique that is different from classical algorithms, and it's not available to classical algorithms at all. We then want to apply a quantum circuit. We learned yesterday what quantum circuits were. There's some series of gates. Maybe they're 1-qubit gates, like the X gate or the H gate. Maybe they're 2-qubit gates, like the C0 gate that we saw yesterday, but it manipulates the input state in some way. And the goal is to use something called interference, which we'll talk about later, to make the outcome we want more likely. And finally, we measure the output. But as we saw yesterday, when you measure qubits, when you measure a quantum state, you don't always get the same answer. So we have to do this whole process multiple times in order to find the most probable outcome. And the goal of a good quantum algorithm should be you put in some input, and then the output, the most likely thing that you measure, will be the solution to the problem. Now, this is very different from a classical algorithm where you just get the answer out at the end. And it's a completely different paradigm for computing. Just like yesterday, we had our spaghetti computer or our pendulum computer worked on completely different principles than an ordinary computer that you're listening to this seminar on. Quantum algorithms are working in a completely different paradigm. So the aim is not necessarily to just get the right answer to pop out immediately. Instead, we have to measure multiple times to find the most probable outcome, which should be the solution to our problem. And you'll see how all of this works as we go later in today's session. Now, why we want to use quantum algorithms is what Stefan talked about yesterday. Specifically, quantum computers provide new algorithms that can be exponentially faster than classical computers at certain tasks. And these tasks include simulation, optimization, or machine learning. And we'll see some examples of all of these later. Now, you can see from this graph that for small problem sizes, usually classical algorithms run faster than quantum algorithms. But quantum algorithms are in a totally different class. So when the problem size gets big, they're able to solve the problem faster, at least in principle, than any classical algorithm could. It's not that we're modifying classical algorithms, it's that we have completely new algorithms that that can be faster than classical ones. And we'll see some examples of that today. So you don't need to get the details on this slide, but this is a picture of the landscape of quantum algorithms. So you'll notice there's blue ones and there's green ones, and we're going to see both of these today. The blue ones are called variational quantum algorithms, and that's something we'll get to in the second half of today's talk. In particular, these are good for NISQ algorithms. Now, think back to the end of yesterday's discussion. We talked about NISQ, which is noisy intermediate scale quantum computing. These are things that we can do when the quantum computers have a lot of noise. We can't fully control perfectly all of the qubits in the way that we would like to. These often combine classical and quantum computing architectures, and actually often combine quantum computing with high performance computing. And these are the ones that are most likely to be useful in the short term. These are very good for quantum physics simulations or material science. They're good for optimization algorithms, solving differential equations, machine learning, things like that. Then there's the green algorithms. These are actually a little easier to understand most of the time, but they're fully quantum. They're very useful for more sophisticated quantum chemistry or linear algebra, more elaborate machine learning or differential equations, or for search algorithms, or for factoring integers. And factoring integers is a really big problem that underlies all of cryptography. However, these green algorithms, these purely quantum or essentially purely quantum algorithms, require us to be able to run really long quantum circuits. And in order to do that, we need to keep errors in qubits under control. So that's something that goes into the fault-tolerant era, which is essentially when we have enough control over our qubits that we don't introduce too much error if we run the quantum circuits for a very long time. So we're going to give you an example of each of these today. And at least for small problem sizes, we'll be able to run both of them on the IQM quantum computers. So the outline for today looks like this. We're going to start with the Bernstein-Vazirani algorithm. The nice thing about this algorithm is that it doesn't have many steps, and it's provably better than any classical algorithm. You can mathematically show that this will, for large problem sizes, always do better than the best possible classical algorithm you have. And we'll use this to see how quantum parallelism and interference work very explicitly. For the second half, we'll turn to variational quantum algorithms. And in particular, we'll give the example of QAOA, which is a hybrid algorithm that combines both classical and quantum computing, and it may be very useful in the short term or the near term for optimization problems. And we'll have an example of such an optimization problem later on. Then we'll take a short break. And then in the lab, you're going to implement Bernstein-Vazirani on our quantum computers and then try using QAOA. IQM has packages that automate a lot of QAOA and make it very easy to use on the quantum computer. And so that is a great opportunity to use a bit more sophisticated of an algorithm yourself. All right, so with that, let's turn to our simple quantum algorithm, Bernstein-Vazirani. Before we get any further, we want to know what the problem we're solving is. So we know that there's some secret code. And this secret code consists of n bits, 1001010, something like that, some sequence of ones and zeros. And we're also given a black box, or what we call in quantum algorithms an oracle. So the question is, what does this black box do? We input n qubits. Those qubits are going to be our guess. And we're also going to input an answer qubit. Now, what this black box does is it takes let's say we've got a 3-bit secret code. So we have 3 qubits, which we'll call Z0, Z1, and Z2. Those are just our 3 input qubits. And they get fed into this black box. We don't know what the black box does, but it takes 3 qubits as input. And then it takes 1 extra answer qubit. And let's say that this answer qubit starts out in state 0. Now, what does the black box do? It looks at the input, and it compares it to the secret code. Every time that a 1 in the guess matches a 1 in the code, it flips the answer qubit. And so then it outputs the answer qubit, and it doesn't change the input qubit. Okay, so we'll see an example of this in just a second. The important thing to know for the moment is that the oracle is going to take in these input qubits. It's going to compare it to the secret code, do something to the answer, and spit out the answer and answer qubit and the input qubits. So the goal of the problem is to identify the secret code by experimenting with the oracle, because nobody's told us the secret code. We just know that there is one. So let's see this a little bit more concretely. So imagine that our secret code is 110. So I'm representing the code in the center of the black box here, and the input on the left, and the output on the right. So what this is going to do is it looks at the, oops, sorry about that. My animation got a little bit messed up here. So the code is going to look at the first input qubit, which is a 1, and the first code qubit, which is also a 1. It says, aha, both of these are a 1. It's matching and it's a 1. So I'm going to flip the answer qubit. So it starts out as a 0, and then it becomes a 1. But then it looks at the second qubit. It says, aha, the input is a 1, and the code is also a 1. So I flip the answer qubit again. So that means that we've flipped the answer qubit twice. We start from 0, we flip to 1, and then we flip back to 1. Sorry, back to 0. And then we look at the third qubit, and we say, aha, the input and the code match, but it's a 0. So I'm going to ignore that. It doesn't matter because that they're matching. It's a 0, so I don't do anything. So this black box flips the qubit twice. Once for the first one that matches, once for the second one that matches, and nothing for the matching zeros. So our answer qubit got flipped twice, so it spits out 0. So nothing happens to the inputs or the answer. Let's see another example. Let's say instead we guess 0, 1, 1. This one doesn't match the code. So what does the black box do? It looks at the first qubit and it says, aha, my input and my code don't match. So I do nothing. Move on. Now we go to the second qubit. It says my input and my code match, and it's a 1. So I flip the answer qubit. It started as a 0, now it's a 1. Then we go to the third qubit, and we say, aha, the input and the code don't match, so I do nothing. So in those 3 comparisons, we flipped the answer qubit once. So that means if we put in 0 for the answer, our output for the answer should be 1. That's on the bottom line there. Now, everyone take a moment. Imagine that we input the guess 1, 1, 1. The black box is going to spit out the answer qubits, 1, 1, 1. But the guess qubits, 1, 1, 1. But what does it do to the answer qubit? Does it spit out a 0 or a 1? Take a moment to think about that, and then put your answer into chat. Good, I'm seeing a lot of zeros and a few ones. Good, that's absolutely right. So the answer we get out should be 0. Why? We have the code and the input match on the first 2 qubits, and so the answer qubit gets flipped twice because both of those are 1s. The third qubit doesn't match between the code and the input, so nothing else happens. So the black box should spit out 1. Sorry, should spit out 0. There's 2 flips. Good. So now you have a chance to experiment with this black box yourself. So you're going to be able to choose the inputs and the outputs, and we've hidden a secret code. So without using a quantum computer, we want you to figure out the secret code. The aim is to play around with it and figure out the secret code yourself, figure out a strategy that's going to find that secret code. And in particular, how many times do you have to put in a different input in order to find the code? How many times do you have to run something through the black box? So I'm going to let everyone play around with that for just a moment, and we can hopefully get the URL into chat as well. Nadia, thank you.
Yes.
So go ahead and use the QR code or the link that Nadia just put into chat. I'll wait here for a moment and then move my screen over to that applet. Oops, I'm in the wrong window. There we go. Okay, yeah, so go ahead and scroll down to the cracking the black box open part here. You get to choose what inputs you want to put in by toggling the inputs here. And you even get to choose what you want the answer qubit to look like. And then if you hit measure, we get answer qubits here. Or sorry, we get the answer qubit and all of our inputs. So go ahead and play around with that for a few minutes. And if you figure out the secret code, go ahead and put it into chat. let's see, what happens if I put in this one? My answer qubit is 1 if I put in 0, 1, 0, 0. I wonder what I can learn from that. Experiment with a couple of inputs here. I'm seeing a lot of 1, 1, 0, 1s. Good. And your measurements are down here. And if we scroll down and see 1101, indeed, the secret code is 1101. And yes, only the last qubit is going to change. We always take the inputs and do nothing to them, but we compare them to the secret code and change the answer qubit. Good. So the secret code is indeed 1101. So how many guesses do you need to figure out this 4-digit secret code? Well, maybe we can figure out a strategy to find the secret code. So one way we can do this is to set one of the inputs to 1 and the rest to 0. So maybe we input, I'm showing three bits here, but it works just fine for 4 bits as well. So just the first input is 1, and we're going to set the rest to 0. So what's going to happen? Well, these input zeros aren't going to do anything, right? If there's an input 0, the black box never ever does anything to the answer qubit. If there's a 1 in the first spot in the secret code, then the answer qubit gets flipped. And so if the answer qubit does get flipped here, that means that there must be a 1 in the secret code in the first spot. Great. But we can repeat this for every other digit. If we input 0, 1, 0, then we compare to the secret code. The only digit that matters is the second digit in the secret code and in the input, because that's the only place there's a 1. That's the only chance we have to flip the answer qubit. And hey, look, in this situation, maybe the answer qubit didn't get flipped. Oh, sorry. Am I sharing my PowerPoint right now?
No, you're actually sharing still
Oh,
the
sorry,
browser.
I'm sharing the wrong one. Let me fix that. My apologies. All right, back to our PowerPoint. There we go. Okay,
Maybe you can once again explain why
yeah,
the
I'll go back.
input is flipped when there is an input 1. That
Yeah,
was a question.
so good. So imagine that we read that this happens. We input 100 into our black box, and the answer gets flipped. What that means is that we've gone through and we've said, okay, let's compare the input to the secret code. So in the first spot, there's a 1 in the input, and maybe there's a 1 in the secret code. Let's say there is. Then we would flip the answer. Now, then we would move on to the second and the third inputs. But the way the black box works, it never flips the answer qubit if the input qubit is a 0. That's just the rules of the black box. It never flips if there's a 0 in the input. So what that means is that our only chance, if we put in 100 to flip the answer qubit, is in the first spot. There's no other way to flip the answer qubit because we don't put in any other ones. So if we find out that the answer qubit did get flipped, that must mean that there's a 1 in the first spot in the secret code, because that's the only chance we have to flip the answer qubit. Similarly, if we input a 1 in the second spot and we find that the answer qubit did not get flipped, that means the secret code must have a 0 in the second spot, because the only chance we had to flip the answer was with the second spot in the code, and the answer qubit didn't flip. That means that there couldn't possibly have been a 1 in the secret code. The only time in the second spot, the only time the answer gets flipped is when the code and the input agree on a 1. And we can do the same thing for every single digit in the secret code. And every spot that we see a 1 in the answer means that there's a 1 in the secret codes. So the first and the third inputs in this case gave us a flipped answer qubit. So our secret code must be 101. So I'm just going to pause in case there are any questions about this that people want to answer me to answer live. Okay, good. So why are there okay, so remember the first n qubits here are the input, and the last qubit is the answer. So if the code is 3 bits, that means we have 4 input bits total. 3 of them are the guess, and 1 of them is the answer bit. Okay. So there's always going to be 1 extra bit that we're using, and that's the bit that gets flipped by comparison to the secret code. The things on the left-hand side are inputs. We get to choose those inputs, just like you did when you were playing in the simulation. You get to choose what you put in on the left-hand side and see what comes out on the right-hand side. So we get to choose, maybe we want to put in 1000 and 0100 and 0010. We get to choose all of those things on the left-hand side. And this is a strategy to solve the problem. Okay, so what did we have to do? For every spot in the secret code, we had to put in a different input because we wanted to set each input to 1 individually. And you can prove that no classical algorithm will evaluate this black box fewer than n times. So F here is what the black box is doing. You put in an input, and you get out some output, and we see how many times we have to put in a different input. We put in 3 inputs if there are 3 bits in the secret code. And no classical algorithm can possibly do better than this. Now, it turns out that quantum mechanics will let us do better. So here we have a different method. So what I'd like you to do is experiment with this link, which we can also post in chat, which lets us play around with this. Oh, I'm seeing a few questions. If the answer bit is 1, that doesn't mean you've guessed the secret code correctly. That's an important thing. So we didn't do a quantum algorithm yet, but if the answer qubit is 1, that doesn't mean you guessed the secret code. It just means that we've gone through and done some flips on the answer qubit, and it turned out you got enough flips to turn it into from a 0 into 1. So the answer qubit is not a you got it right thing. It's just a thing that that the black box is messing with. Okay, so let me swap over to this applet for the moment. Yeah, the answer bit is for checking what's changed. That's right. Okay, so our second applet is right here. Okay, so what we're told to do is to apply a set of H's after the black box. So let's put those H's in there, like this. And we're also told to prepare an equal superposition of all 5 qubits. So we saw yesterday how we can turn a single qubit from 0 into 0 plus 1, which is a superposition of all possible entries for 1 qubit. Does anyone remember how we were able to do that for 1 qubit? Go ahead and put your answer into chat. So C0 is working with 2 qubits. Yeah, I'm seeing the Hadamard gate. That's right. So the Hadamard gate turns 1 qubit into a superposition of 0 and 1. So if we want to do this to all 5 qubits, what do you think we should do here? Go ahead and play around with it and see what happens when you measure. If you scroll down, you'll see the measurements. So right now, our output is giving us all sorts of 6% chances for all sorts of different inputs. That's kind of crazy. That's not very useful. Give you a moment to play. And what happens if I take off this H? Oh man, something else crazy happens. We get a 3% chance for every outcome. All sorts of strange things are happening here. Let me actually make this a little bigger. So instead, let's see what happens if we put in a Hadamard gate on all of the qubits, except for the last one. We just want to, we didn't quite get what we were looking for, but that's looking promising. What happens if we prepare a superposition of all the qubits? If we look at the measurement we get, hey, look, only one output had any chance of happening. 0, 1, 1, 0, 1. Huh. That's crazy. Something very peculiar has happened. Instead of getting an equal chance of all sorts of different outputs, what looks like a random output got 100% probability. In fact, we'll get to the attendance form later. If we open the black box, it has something going on qubits 2 and 3. And if you look down here, qubits 2 and 3 are a 1. And that's the only outcome that had 100% chance probability of being measured. So something magical is happening here. As long as we don't have to look inside the black box, as long as somebody has handed it to us, if we just put these Hadamard gates in, only one possible outcome comes out. And in fact, the 0110 here is the secret code. That's what's encoded in this black box. That's why the black box, if we crack it open, is messing with qubits 1, 2, and 3 only. The secret code is 0110. So let me switch back to the PowerPoint. Over here. So what's happening here is if we put the guess qubits in with a 0, the answer qubit with a 1, and we put Hadamard gates before and after the black box, it turns out, that the output of the guess qubits is the secret code with 100% probability. These 3 are the secret code. Something rather magical has happened. Just by putting these Hadamard gates in, we've somehow instead accidentally messed with the input qubits instead of the answer, but it just told us the secret code without any other work. That's pretty amazing. So we're going to see how this works by putting in just one set of inputs, all zeros except for the last qubit, just doing it exactly one time. We got the secret code just spat out as an answer for us, instead of having to put in a whole bunch of different inputs, one for every guess qubit that we have. So before we get to how this works, here is the attendance document today for today. And so go ahead and we'll put this in chat as well. You can go ahead and sign into the Google form. Thank you, Stefan, for sharing that. So I'll give everyone just a moment to open that up. All right. So with that, how does this magical algorithm work? We want to open up the quantum states and see how it works, where just putting these Hadamard gates, black box Hadamard, is going to get us the answer. So what happens is that the Bernstein-Vazirani algorithm finds the secret code C with a single query of F. So we just put it into the oracle exactly one time. And it uses interference and quantum parallelism. F is our oracle, C is the secret code. So we're going to do a secret code example where there's only 2 qubits in the secret code, and we're going to assume that the secret code is 1, 0. We have to assume we know how it works so that we can see how it works. So on the left-hand side here, I've shown you the quantum circuit that we just played with. So we input 0, 0, 1. We put Hadamards on all of the qubits at the beginning, and Hadamards on the qubits at the end. It turns out that last Hadamard down here, I think I'm missing that Hadamard, and I apologize for that. That is missing in the graphic. There should be a Hadamard on the last one as well. Okay, so what we're going to do is we're going to break this up into steps. We're going to see what happens to the quantum state of all these qubits at each of these spots where I've got a dashed line here. And we're going to track what happens. So we're going to watch at every single step how the qubits change. And so we're going to just focus in on these first 2 spots. So ignore the last ones for now. We'll get to those in the next slide. So our input is 2 zeros and a 1. And what I'm doing here is I'm splitting up the guess qubits, which are the first 2, and the answer qubit, which is the third one, just so that we can see it a little more clearly, which qubits are which. Okay? So that's the same thing as just saying that the first 2 qubits are 0 and the last qubit is 1. Okay, that's just what we input. So let's look at what happens after we apply the Hadamard gates. The key point here is that this is the quantum state we get out. So we know that a Hadamard gate turns the first qubit from a 0 into 0 plus 1. That's this Hadamard gate right here. Can you see my annotations? Good. All right, so the first Hadamard gate turns the first 0 into 0 plus 1. Now, it turns the second Hadamard gate, turns the second qubit into 0 plus 1. That's what's going on here. And the third Hadamard turns the third qubit into 0 minus 1. So why is there a minus there? Hadamard turns the 0 input into 0 plus 1, but our input here was a 1. And so Hadamard turns the 1 input into 0 minus 1 instead of 0 plus 1. So that's why it acts a little bit differently on the last qubit, because we input a different state. So all that's happened is something that we saw yesterday. Our Hadamards are turning 0 into 0 plus 1, and they're turning 1 into 0 minus 1. Okay, but we can do a little bit of multiplication. If you think back to your algebra, we're going to FOIL out those first 2 terms, so we see what happens to the first 2 qubits together. So, for example, this term times this term is both qubits in the 0 state. This term times this term is both qubits in the 1 state. And then there's cross terms that get us into the 1, 0 and 0, 1 states. So all I've done is multiply. But if you look at what we've got here, it looks like we've input all possible inputs, right? What are the possible inputs we could put into the oracle? 0, 0, 0, 1, 1, 0, and 1, 1. All of them are sitting there in that sum. So that means that we've done quantum parallelism. It looks like we put in all possible inputs in parallel, all of them at the same exact time. This is the magic of quantum parallelism. By putting in these Hadamard gates, we get to put in all inputs at once without preparing a new qubit, a new input. All right. So I've just copied over the thing we had on the last slide. This is exactly the same thing on the last slide. You'll notice the bottom equation over here is exactly the same thing as what we have on the next slide here at the top. So I just copied it, but now we want to see what the oracle does. Now, this slide and the next one are going to be the mathiest slides you see all day. So bear with me. Just know that there's going to be a bit of math here. And so we're going to go through it carefully. So we apply the oracle. Now, the oracle is going to do different things to each of these different inputs. So let's start out with what it does to this 0, 0 input. So we compare the 0, 0 input to the secret code, and we look for matching ones. Well, hey, there's no matching ones in the input 0, 0 and the code 0, 1, or sorry, 1, 0. So remember, our code is 1, 0. So what does the oracle do? Absolutely nothing. And so this term does nothing. The oracle does nothing because there's no matches in the secret code. But let's look at what happens when we feed in this last term into the oracle. It compares 1, 1 to the input. And it says, hey, I've got a match. The first qubit of the input and the first qubit of the code match, and they're both ones. So what does it do? It says, I'm going to flip the answer qubit. So if you look at what happened with the answer qubit, which so far has just kind of hung out at the bottom, at the end here, we had this 0 minus 1. But the oracle is going to turn that into 1 minus 0 because we flip the answer qubit, right? Because there's a match between the secret code and the input. Okay, so the oracle did something because there's a match. That's the same thing that we saw before. No quantum mechanics there. But this minus sign that sits in the center here, right? Let me change the color here real quick of my annotation. This minus sign in the center here, I can move over here. And so what has happened is that, and we get back to the same thing here on the answer qubit. So by flipping the answer qubit, what we actually did was put a minus sign on this special input. That's peculiar. We've taken, by flipping the answer qubit, we moved a minus sign onto the input qubits. This can't happen for classical bits. Those minus signs don't even make any sense for classical bits. This is the real quantum mechanics here. And what this does is this puts a minus sign on the terms where the oracle does something. In particular, they're the places where there's a 1 in the first bit of the input, the first bit of the guess. This is called phase kickback. The pattern of minus signs that we get in the secret code, or sorry, in the input here, after we apply the oracle, comes from the secret code. The secret code looks at the first spot here, and it says, aha, I have a match on the first spot with where there's a 1 in my secret code. So I'm going to put minus signs into those terms down here. So we get these minus signs that come from the secret code. That's called phase kickback. And those minus signs are truly quantum mechanical. We'll see how they help us in just a second. All right. So by applying the oracle to this special state that we've prepared, we got a bunch of minus signs. So let's see what happens now. So I've just repeated the circuit, and we're going to focus on the last part of the circuit. And we applied some Hadamard gates to it. So here we are. We're applying Hadamards on the first 2 qubits. I'm going to ignore the last qubit for the moment. It doesn't really make too much of a difference in the end here. And we're going to apply those Hadamards to the state that we just had after applying the oracle. So here, this psi2 is what we ended up with on the last slide. So I've just copied over what we had on the last slide. And we're applying these 2 extra Hadamard gates to it, which live over here. Okay, so how do we apply 2 Hadamard gates to this messy, messy thing? Okay, I'm going to give you an example. And again, one of the mathiest slides, so bear with me. But we get a ton of outputs here. So you can check the math here. And we're going to focus in on one piece of it. So we're going to focus in on this first one where there's an input of 0, 0 here. And we're applying on the first 2 qubits, and we're applying these 2 Hadamard gates. Now, if you do something similar to what we did earlier, you can go ahead and check that the output looks like this, right? 0 turns into 0 plus 1 from a Hadamard. And so this is just the same thing we did at the first step. We take this 0, 0, and we turn it into a sum of all the possible inputs. Now, if you go through and do some more math, similarly, you can see that when you apply 2 Hadamards to 0, 1, you get the same thing, except there's these important minus signs here. Oops. And that just comes from the Hadamard gates. Nothing from the secret code, just the Hadamard gates. And we can do this for all of the different pieces, like this. Okay, that's a lot of different math and a lot of different terms. The things that I want you to pay attention to is that this minus sign is this minus sign, which is the same thing as this minus sign. So those minus signs came from the secret code. These 3 minus signs also came from the secret code. The rest of the minus signs just came from Hadamards. Yes, there's a question.
Yes, we have a question from the audience, which I think makes sense to answer for all of us, because it's a very good one. The question is, who knows the oracle and who provided it? And I think this
that's
is
an
an
excellent
question.
That's a very, very good question. So we imagine that a friend of ours wanted to send us the secret code. So they made the oracle, and they sent us the oracle. Now, if you know the secret code, you can make an oracle yourself. But if you don't know the secret code, you can't. And so we just imagine that some friend made the oracle, sent it in the mail to us, and said, here, go ahead and play around with this thing. Yeah, that's an excellent question. Good. So we saw all these minus signs turn up. Why do I care so much about the minus signs? The reason is this. To get the total state at the end, the final output state, we have to add up all of these different terms because they're added up over here, right? We add up all of these terms and we apply these H gates to each term. So we have to add them all up. And if you look super carefully, this 0, 0 has a plus sign. This 0, 0 has a plus sign. This 0, 0 has a minus sign. And this 0, 0 also has a minus sign. And those minus signs come from the secret code. So we've added two terms that are positive and two terms that are negative. So they cancel out. They disappear, and that's going to disappear completely. And if you go through and you do that counting very carefully for every single output, what you find is that the only output which doesn't have two positives and two minuses is 1, 0. And 1, 0 is the secret code. So these minus signs that came from the secret code end up with this really complicated, weird pattern of minus signs that happen in the end. But if you add them all up, the only thing that doesn't have two positives and two negatives is the secret code. And so that means that everything cancels out unless the input qubits are exactly equal to the secret code, in which case all of the outputs add up and we have something left over. This is the phenomenon of interference, where positive and negative outputs cancel out, and which is called destructive interference, and positive outputs add up. And so we get more probability to have the output we want, which is the output that's the secret code. So this minus sign thing, this very, very quantum phenomenon of getting all these crazy minus signs that I've described for you, is what helps us make it so that only the right output comes out. And so by just inputting one particular guess, 0, 0, 1, it just spits out the right thing because we've canceled out all of the other possible outputs. And nowhere in here did we actually have to know the oracle. We just had to apply the oracle. We just saw how it worked. We just assumed we knew the oracle so we could see how all of these minus signs come out. So this is what makes it a really quantum algorithm. So the end result here is that the answer qubit is in the state 0, -1. That's for the answer qubit. Sorry, I flipped the order of this around. My apologies. And then the other qubits are in the state that's given by the code, which in this case is 1, 0. So that means that by measuring the n qubits exactly once, all we have to do is measure these code qubits. There's no, these output qubits. There's no superposition left for the output qubits, just for the answer, which we don't have to worry about. We measure them once and we're guaranteed to get our secret code. And remember, we had to do that many, many times in order to, without using quantum mechanics. So that's the result of the Bernstein-Vazirani algorithm. By only preparing one set of input qubits, we can measure them once and always get the secret code out. So let's summarize what we've learned. Qubits leverage superposition to represent and process multiple states concurrently. We added together all of the different possible inputs. This superposition, together with entanglement, which we talked about yesterday, allows quantum algorithms to explore many possible solutions or solution paths in parallel with a single computational step. So we put in all possible inputs, and we got to apply the oracle to all possible inputs as well. Then, by being very careful about how we use those minus signs, we could use quantum interference to amplify the correct solutions and suppress incorrect solutions. We want all of the bad solutions, which aren't the secret code, to cancel out, and the only one that's left to be the correct solution, the secret code itself. And these effects are what let us speed up compared to classical algorithms. All right, so that's the end of the Bernstein-Vazirani section. And this is really incredible because it says something where we had to put n different inputs in for the classical solution, only needs one input for the quantum case and one measurement, which is really quite incredible. Now, if you have noise, that one measurement thing might not quite work. You have to repeat a few times to make sure that noise didn't come in and mess you up. But at least in principle, with a perfect quantum computer, you would only have to measure once. So we're now going to switch gears a little bit to a different type of algorithm called a variational quantum algorithm. So this is a totally different class of algorithms that works for a different class of problems. So let's step back and talk about a different class of problems. So many problems that are interesting to solve are expressed as minimization problems or maximization. Maximization also works. So for example, you might want to find a path to drive somewhere that takes the least possible time. That's what your Maps apps are doing constantly on your phone. They're trying to find paths to drive on that take the least amount of time. Or maybe if we're doing chemistry, we might want to find the lowest energy configuration of electrons in a molecule. Or maybe we have a stock portfolio and we want to set it up so that we minimize the possible risk. So all of these things, we want to find the lowest of something. We want to minimize something. And that's an interesting set of possible problems. So we're going to call the thing that we want to minimize a cost function. So for example, a driving route, the cost function is the time you're driving. Or in a molecule, the cost function is the energy of the electrons. In a stock portfolio, the cost function is the risk. And the goal is to minimize that. So there's this magical thing called the variational principle. And it says that if you make an educated guess for the solution to the problem, so let's just pick a driving route and figure out how long it's going to take to drive on that route. We're going to make an educated guess for the solution. We're going to pick that route. We calculate the cost function. The closer the cost function is to its minimum possible value, the variational principle says the closer your guess is to the true solution. So if we have two different driving routes and one of them takes less time than the other one, then the variational principle says roughly that our answer should be closer to the true solution if we choose the one that takes less time. It might not be the least time, but it's closer to the least time. Now, there's some caveats and whatnot on that, but that's the general idea of the variational principle. And so variational quantum algorithms use the variational principle to find the best possible approximation of the true solution of our problem. So what they're trying to do is they make some guesses, and then they try to make that guess better and better and better over time so that we get closer and closer and closer to the optimal possible solution. And this is actually really interesting for noisy intermediate scale quantum devices, so NISQ devices, because it involves in the exchange of quantum and classical information in a way that we're going to see very soon. And this is useful because we can use very good quantum classical computers to amplify the results or to improve the results of our quantum computers. And also, these algorithms tend to be pretty noise resilient. So even if your quantum computer has a lot of noise, your qubits, you can't control your qubits super well, these algorithms still tend to work pretty well. So we'll see how this works. So here's the overall flow of variational algorithms. So we're going to take these things one piece by one piece. Basically what happens is we make an initial state, we input it into something quantum called the ansatz. So these left-hand two sides tend to be quantum, run on the quantum computer. We make a measurement, which is very quantum, and we feed the results of that measurement into the cost function, which is the thing that we're trying to optimize. And then we feed that into a classical optimizer. So on the right-hand side here in red are the pieces that tend to be classical. And on the left-hand side in green and blue are the parts that are quantum. And so we'll unpack this a little bit over the next 25 minutes or so. So let's focus in on the cost function. Remember, the cost function is the thing that we want to optimize. So let's try to understand a problem that we could apply this sort of algorithm to so that we can understand what we're optimizing better. So we're just going to start from a problem, no quantum mechanics yet. Okay, so this problem is called the max cut problem. So imagine that you're proctoring an exam. You have a bunch of students taking an exam, and they have two rooms. And you get to decide what room each of the students go into. But these students like to cheat. They're not very honest students. And students who are friends and in the same room are more likely to cheat. It's a lot easier to go, try to signal to your friend if you're in the same room. And you're more likely to cheat with someone who's a friend, right? And imagine that you know which students are friends. You've been paying attention to all the people in your class. So here's the goal. Assign each student a room so that you minimize the chance of cheating. That is, we want to split up as many friendships as possible, right? We want to make it so that if two students are friends, we have the highest chance of possible as having them in different rooms so that they're unlikely to cheat. So we can represent this problem in a particular way. A standard way to do this is with a graph. So here we just have a circle, which is called a node, and each of these represent a student. So you see here we have Alice, Bob, Charlie, Diana, Eve, and Frank. There are 6 students in this example. And each line here is a friendship. So the way to read this is that Alice is friends with Bob, and Alice is friends with Charlie, but there's no line connecting Alice and Diana, so Alice and Diana are not friends. And we have this encoded for every person here. Right? And the goal is to assign them all of these 6 students rooms so that we split up as many friends as possible, just for the exam. They're welcome to be friends, but we don't want them cheating on our exam. It turns out that this problem is NP hard in general. That means that it's very difficult for classical computers to do this efficiently. There are some pretty good classical algorithms, but it's very difficult in general. Turns out quantum computers can do this pretty effectively. So remember what we talked about with cost functions. That's the thing we want to optimize. So in order to turn this into a problem we can solve on our quantum computer, we need to determine a cost function for this problem. So a cost function converts a guess at the answer into a single number. The lower the output, the closer to your best solution you are. And so for max cut, what's a cost function look like? We're given the list of friendships. We input a list of students which are in which rooms, and we output some number. So for example, we imagine we put Diana into room 1 and all of the other students into room 2 for Diana. We would see that there are 2 friendships that are broken up. Diana and Charlie are friends, and Diana and Frank are friends, and they're in separate rooms. But there's a bunch of friends who are all in the same room. They're all in room 2. So whatever this setup is on the left, that should have a pretty high cost because it doesn't do a very good job at solving the problem we want. On the right-hand side, we have a different arrangement of the students where Diana, Charlie, and Eve are in room 1, Alice, Bob, and Frank are in room 2. And there we see that only 2 friendships are in the same room. Most of the friendships are broken up. So these 2 friendships are in the same room, but all of these friendships between Alice and Charlie, Charlie and Bob, so on and so forth, are in different rooms. So those are broken up. And so that's a better solution to the problem. And so that should have a lower cost. So for example, our cost function should maybe say this arrangement on the left, maybe it has a cost of 3. And on the right, it has a lower cost, maybe -1, because it's closer to the real solution. So we want to design our cost function so that better solutions give us lower answers from the cost function, and we want to be able to calculate it efficiently for any input state on our QPU by measuring our qubits. So don't worry too much about that property right now. Right now, I would like you to take a little bit of time to experiment with the max cut problem. You can try sorting the students into different rooms yourself using these links. And the aim is to figure out how to encode the problem into a cost function. We want to input the list of friendships and the rooms that the students are in, and we want to output a number that gives us some idea of which friendships, how many friendships we've broken up. So I'll let everyone get to that and then experiment for a little bit, and I'll go move over to that myself. And if you want to click and drag the students into different rooms instead of representing them by colors, there's an option for that as well. Let me change what I'm sharing. Oops. Right. So for example, if I turn on room mode here, I can start dragging some of these people into different rooms. And if I do this, I see I've broken up all but 3 friendships, so that does okay. Things like that. Go ahead and experiment. Yeah, so here we see that we've tallied up, we have 4 separated friendships and 3 friendships in the same room. Good, and I'm seeing some people are finding that they can get a solution where there's only 1 friendship in the same room, which is absolutely correct. That is the minimum you can possibly do. And in fact, let's see if I remember exactly how this goes. I think we want to do this. Yeah, so an arrangement like this, I think there's a couple of different solutions, but if you put Alice, Charlie, and Frank in one room, and Bob, Diana, and Eve in the other room, you'll find that there's only 1 friendship in the same room. So just watch Alice and Charlie really carefully to make sure that they don't cheat. Okay, but how do we turn this into a cost function? We want to be able to say, I've listed out the rooms for you. How do we actually get a number? So what we want is for that number to tell us something about the number of separated friendships. So let me go back into my PowerPoint. So what we can do, for example, is to assign each student a qubit. 0 means that students in room 0, and 1 means that the students in room 1, or you can label the rooms 1 and 2, but for our purposes, it might be a little easier to call it rooms 0 and 1. So we're going to define this cost function. And let me explain what this cost function means. Just bear with me for a moment. So our students are labeled by I. So in this case, we have 6 students. So I is going to run from 1 to 6. Zi is 1 if qubit I is in state 1, and Zi is -1 if qubit I is in state 0. So what that means is we're saying if there's a student in room 0, they get a -1, and if there's a student in room 2, they get a +1. Now, if we multiply together the Z's for a pair of students who are friends, let's see what happens. If the students are in the same room, their Z's are either both +1 or both -1. So when we multiply together, that gives us a cost of 1. If the students are in opposite rooms. One of them has a z with 1 of 1, and one of them has a z of -1. So when we multiply them together, they're in different room. If they're in different rooms, the product is -1. And so the cost function gets a -1. So friends in the same room give us a cost of +1. Friends in a different room give us -1. So if we add up the cost for all the different pairs of friends, then broken up friendships get us strong negatives. And that lowers the cost. And friends in the same room increase the cost. So we get the lowest cost when we maximize the number of split up friendships. So over here on the right, you can see we have 5 unbroken friendships in the top example and 2 broken friendships. So that gives us 5 minus 2, which is +3. And on the bottom, we have 6 broken friendships and 1 unbroken. So that's a cost of 1 minus 6, which is -5. So this z thing is just a way of encoding which friendships are broken up and which ones are not into the state of each qubit, right? All we need to know is which room each of them are in, and then we can calculate the cost function from that just by plugging in a bunch of +1s and -1s. So this is a good cost function for this problem because it's as small as possible when the number of split up friendships is as big as possible. We are close to our goal, right? And it turns out that this cost function is actually easy to calculate with a quantum computer. All we have to do is measure our qubits and then do some classical calculation. It's very easy. We'll actually implement that a little bit later in the lab. Okay, so that's how the cost function works for these variational problems. And we now have a problem in mind that we can solve with a variational algorithm, this max cut problem, the problem of splitting up these friendships. Now, let's look at the next part of the algorithm, which is called the Ansatz. Okay, the goal of a variational algorithm is the following. We're going to encode possible solutions to the minimization problem as quantum states. Sometimes this is actually really natural. In quantum chemistry, the solution is often literally the quantum state of a bunch of electrons or atoms. So that's very natural to talk about encoding into a quantum states. We just saw a way to encode possible solutions to the max cut problem into quantum states, right? Possible solutions are assignments of students to rooms. And all we have to do is say that a student is in one quantum state if they're in room 0, and in a different quantum state in room 1. So that's an easy way to encode possible solutions to this problem into qubits. Our goal is to find a quantum circuit that turns some initial state, we haven't specified what it is yet, into the approximate solution of the minimization problem. So we start with some initial state, we apply a quantum circuit, and our output, ideally, is very close to the solution of that minimization problem. Unfortunately, there are infinitely many quantum possible circuits, and for that matter, infinitely many possible answer states as well, for some number of qubits. And so we can't possibly try all quantum circuits, right? Ideally, you would just say, okay, I'm just going to try all the possible quantum circuits and see which one gives us the lowest cost. But you can't do that. You can't apply infinitely many quantum circuits. We just don't have the time. So what we need instead is an ansatz. So here's an example of an ansatz. So this is a very simple ansatz. We start with the qubit 0. We apply a Hadamard gate, and then we apply a particular gate, which is a rotation gate around the z-axis. So we're on the Bloch sphere, and we rotate our state around the z-axis by some angle. The idea here is that θ2 is a parameter. It's just a number, and it can be any angle. So there's many different possible quantum circuits here, right? For every different theta 2, there's a different quantum circuit. And together, this is a collection of guesses. All possible different theta 2s give us a collection of guesses. So an ansatz is a collection of guesses for the solution to a problem. And for us, it's actually a collection of quantum states or a collection of quantum circuits. Either way, we can talk about it in the same way. This is just any guess. It can be a random guess or an informed guess. So let's look at what this looks like. So let's go back to our block sphere from yesterday. What possible quantum states can we represent using this ansatz? What gets output from this ansatz? So here's our block sphere, and it turns out that any state along this red ring can be outputted from this circuit. Different states come from different theta 2s. So maybe theta 2 equals 0 is over here. So theta 2 equals 0. And maybe pi over 2 is over here. Pardon my writing on Zoom annotations. And so there's different possible values for theta 2 that give us different quantum states. Now, we have to figure out whether this is a useful guess or not, right? This is not every possible quantum state is in this ansatz. We haven't guessed the state 0, for example. So take a couple of moments to think about what properties you might want an ansatz to have. If I give you a problem, what might it be useful to have an ansatz be able to do? What would make it a useful guess for a particular problem? So think about that for a moment. And go ahead and maybe type an answer, any answers you have in chat. Good. So I see we want to get the maximum number of circuits with the lowest number of parameters. That's a great idea. We want it to be able to optimize the cost function. So hopefully our ansatz should contain the solution. It'd be really weird if our ansatz didn't have the solution. We want to be able to account for constraints or boundary conditions. Yes, these are all great answers. Linear, okay, so linearity might be helpful. It depends on the context, but yeah, we might want it to be linear. We might want it to explore all over the block sphere. Yeah, so that we can get all possible answers. That might be useful. I'm seeing a lot of good answers here. Yeah, so I've got a few of those answers prepared, but other people are giving all sorts of other good ones. So we should be able to compute with this ansatz pretty easily. If I have to do a really complicated quantum circuit, then that's going to make it really difficult to work with that ansatz on our quantum computer. We hope that the ansatz actually includes the solution to the problem. I'll talk about that more in just a second. We want it to be easy to work with on the hardware and not have too many parameters. So let's explore the actually containing the solution part a little bit further for the moment. So here's this slide I just gave you, and here's our block sphere. So this is a really good ansatz if the answer to our problem happens to be, say, here. That means all we have to do is pick the right theta 2, and we'll get really, really close to the actual solution to our problem. But what happens if the actual solution to our problem is this purple arrow somewhere over here? Then no matter what theta 2 we pick, we're never going to have a quantum state that actually gets us close to the solution of the problem. That's not helpful. So this is in so the idea here is that if this box represents the complete set of quantum states, different ansatz will be able to cover different parts of that that set of quantum states. So for one qubit, that set of quantum states is the Bloch sphere, but this is just kind of an abstract representation. And our hope is that the solution sits with our ansatz. So if the solution of the problem is here, we would want to use ansatz A. Ansatz B doesn't get anywhere close to that solution. But if the solution of the problem is over here, we want to use ansatz B, because solution ansatz A doesn't get anywhere close. If it's here, either ansatz will work. And if it's over here, we should probably find a different ansatz. So we want our guess to hopefully be able to get close to the solution of the problem. So here's another possible ansatz. We do two different rotations to our qubit. So theta 2 and theta 3 are classical parameters. And it turns out that choosing just a few different values of theta 2 and theta 3 actually lets us get all sorts of different states that are all over the Bloch sphere. We don't have to pick a lot of different values for theta 2 and theta 3. So this ansatz, no matter where the solution is, will get close for some values of theta 2 and theta 3 to the solution to our problem, because it covers the entire Bloch sphere very easily. And so we want, with as few values of theta 2 and theta 3 as possible, to get as dense as possible of coverage on the Bloch sphere so that we can approximate any solution we want. The idea here is expressibility. This is a measure of the power of an ansatz to generate a uniform set of states in a space of quantum states. So let's compare our two ansatz. We can't get, on the left-hand side, that ansatz only gets a few quantum states. It's only the ones on the equator of the Bloch sphere. So it has low expressibility. It can't get all possible quantum states. On the right-hand side, though, we have high expressibility because it's very easy to create all possible quantum states using this ansatz with only a couple of quantum gates. So it's currently an open question how important expressibility is for variational quantum algorithms. So we believe that expressibility is important, but nobody's actually been able to prove anything, prove really concrete results, like really sharp results about this. So because we're low on time, I'm not going to take some time to play with this expressibility here, but you can go ahead and look at this link yourself to play around with the expressibility of different quantum circuits. So how do we choose our ansatz, our guesses? There's two different ways to do this. One is problem-inspired. They're good for one particular problem. So quantum chemistry, for example. So there's this unitary coupled cluster ansatz, which is very complicated. It's in this picture here, but it's very specifically inspired by guesses that based on what we already know about quantum chemistry to try to make our guess state closer to what we expect. There's also problem agnostic ones and the goal there is to be hardware efficient. We want to make not too complicated of quantum circuits, and we want to use what are called native gates and account for connectivity. So I'm going to talk briefly about this, and I'm a little low on time, but we're going to talk more about this tomorrow when we discuss transpilation, but that's what we're trying to avoid there. So let's just take a quick look at this and just do a quick overview of hardware efficiency. So our Garnet quantum QPU is shown on the right-hand side. So the dots are the qubits and the boxes are the couplers. So take a look at this circuit and try to tell me which one is efficient for our Garnet QPU. So go ahead and put your guesses into chat. So notice here that we have qubit 1, qubit 2, and qubit 3. So go ahead and take a look at which qubits are talking to which qubits when we do this, if we're applying this to qubits 1, 2, and 3. So I'm seeing a mix of A's and C's here in particular. Good. So let's take a look here. We have qubit 1, which lives over here. Qubit 2, which lives over here. And qubit 3, which lives over here. So if we have qubits 1 and 2 talk to each other with a gate over here, then, hey, look, qubits 1 and 2 talk to each other on garnet. But if we try to have qubits 2 and 3 talk to each other, qubits 2 and 3 are actually very far away from each other on garnet. So they don't talk directly. And so implementing that is going to be very complicated. So we want to choose circuit A. And I'll mention this native thing in just a moment. We want to choose circuit A because qubits 2 and 3 aren't coupled on garnet. We don't want to have qubit 2 talk to qubit 3 if we can avoid it. Now, I'll just mention also that CX, the controlled NOT gate, is not native to IQM hardware. IQM hardware likes to do control Z gates, which are these double dot gates here. So we would try to avoid using controlled X or controlled NOT gates as much as we can. Now, I just want to mention that this circuit is that the expressibility of this circuit is limited. It can't entangle qubit 3 with qubits 1 or 2. So there's only certain things that we can do with that. Okay, so now let me just mention briefly where to start. We need to input an initial state that we're going to apply our quantum circuit to. This also has a few different possibilities. One is that there's no special requirements. So for example, we can just put in all qubits in state 0. That's a perfectly fine initial state. But we could also choose, for example, reference states. So in quantum chemistry, there's a state called the Hartree-Fock state, which is kind of a natural starting point, which tells us, shows up in a lot of places in quantum chemistry. So it seems like it might be a sensible place to start with the state. And that just comes from the problem. So maybe the problem has a really normal standard reference state that has something to do with the class of problems you're interested in. You could also do something more problem specific, like a feature map from machine learning. So in a machine learning context. The initial state can be random or an educated guess. Either one is okay. The performance, you have to experiment in order to find how the performance of the algorithm works. So let's go back to our algorithm here. We have an initial state that we feed into a quantum circuit. We measure that quantum circuit, which goes into the cost function. And then that cost function has to be minimized. Our goal is to optimize that cost function. So the goal is to choose the parameters in the ansatz so that we lower the cost function as much as possible. We choose the right thetas, theta 2 and theta 3. So the classical computer in this context determines how you adjust the ansatz parameters to decrease the cost function. This is a standard problem in classical computing, optimization of a cost function. And there are a couple of classes of methods which we don't really have time to talk about today, but this is all implemented for you in a lot of libraries. Some of them are called gradient-based methods, and some of them are called gradient-free methods. The gradient-based methods basically tell us how to change the parameters to make the cost function drop as fast as possible. So if you imagine you have a topographic map of your parameters where the peaks and valleys tell you about where the cost function is high and low, the aim of the gradient-based method is to go downhill as fast as possible. We just want to go right down the hill to the bottom of the valley so we get the lowest cost function as possible. It turns out that slightly different methods are efficient to compute this gradient using classical versus quantum computers. On quantum computers, we use something called parameter shift rules, which you can look into yourself if you are interested in that. There's also what are called gradient-free methods. So one such method is called particle swarm optimization, but this is useful for certain sets of problems where maybe it's easy to get caught in a false minimum on a gradient-based method. But there's a lot of active development here on integrating the classical computer, the classical optimization of these parameters with the quantum computer. Now let me finish up by talking very briefly about a couple of well-known variational quantum algorithms, and we'll explore one of them soon. So this is the structure of our quantum algorithms. And lots of different ansatz, lots of different cost functions, and lots of different optimizers give us different algorithms. So for example, one of them is called a variational quantum eigensolver. And this is an algorithm whose goal is to find the lowest energy state of a quantum system, so molecules or materials or an atom. The way it works is that we express the problem's Hamiltonian energy in qubit operators. It turns out that there's some subtleties here because atoms and electrons aren't qubits, so we have to figure out how to encode that into, sorry, one moment. Let me fix that up for a second there. Atoms and electrons aren't actually qubits, so sometimes you have to do some careful things to encode the energy in qubit operators. Then we prepare a quantum state using a variational circuit. We evaluate the average energy of that state on a quantum computer, and then we update the parameters to minimize the energy. This is very useful for, particularly for molecular ground state energy estimations. Another one is called QAOA. It's the Quantum Approximate Optimization Algorithm. And this is what we're going to be using in lab. It solves certain combinatorial optimization problems. So think MaxCut, the student sorting problem that we had earlier. And the idea here is that there's a very specific structure to the ansatz, where there's layers of the ansatz. We apply a quantum circuit that has something to do with the cost function, which is over here, to the input state, then something called a mixer Hamiltonian, a mixer operator that adds quantumness to that state. And then we repeat that many times in many layers, and then we measure our cost function at the end. And then we're going to measure that cost function, optimize the parameters, and repeat until we've gotten to the lowest possible value for our cost function. And that we're going to learn more about in lab, but it's useful for MaxCut for things like financial portfolio optimization and scheduling problems. So I ran a little bit over, but let me wrap up. So variational quantum algorithms are hybrid quantum classical algorithms that use an ansatz, a parametrized quantum circuit, and classical optimization to solve complex problems. The key components are the ansatz, which is the quantum circuit, the cost function, which represents the objective of the problem, and the classical optimizer, which updates the parameters in order to minimize the cost function. And then we had a couple of different examples of popular algorithms, which we use to solve different types of problems. So with that, let's take a 10-minute, let's do a 10-minute break, and then we'll come back for lab. If you would like to start getting set up on the lab while we, oh, sorry about that. We don't actually need to, I have an unnecessary instruction here. From if you would like to get started on getting set up on the lab now, please feel free. And the URL is here, and we'll stick around to answer some questions during the break. So let's come back at 50 minutes after the hour for those of you who are on most time zones. If you're India or one of the other time zones that's shifted by a half hour from like Europe, that will be 20 minutes after the hour. All right, let's see. How to convert a problem like traveling salesman problem to a Hamiltonian. That's an excellent question. So that's actually going to be very similar to what we did for max cut. So but there's a little bit of extra work that you have to do. So the idea is that actually for every for every city that the salesman travels to and every time step, you need 1 qubit. And then you have to add some constraints. So it's a little bit more involved than the max cut problem, but it is something that you can do to convert to a Hamiltonian. You just need the number of qubits that you need actually grows pretty quickly with the number of cities that you're visiting. Yeah, so the traveling salesman problem can be solved using a quantum computer, but it's not in polynomial time. Um, so there's no, so I believe if I don't quite does anyone else remember the status of any proven speed ups or anything like that for traveling salesman
I think
problem?
the challenge with traveling salesmen is that you have very good classical heuristics that do
Yeah.
it pretty well. That's why no one would really look into this problem on a quantum computer, but like more consider more complex problems.
Mhm. Yeah, so I think a lot of scheduling problems are, oops, I didn't mean to dismiss that question. Sorry about that. I think a lot of like scheduling problems are essentially complicated versions of the traveling salesman problem.
There is a question about how would we measure complexity like we do in classical computation. I think that answer is pretty simple. It's pretty much the same. You count steps.
So submitting the jobs on residence for the certificate, you just need to do that before the next session. So before tomorrow's session. And we'll start up again in about 5 minutes. So with credits in the interactive notebooks, only when you submit jobs to residents, so the lines that say something like get measurement, parentheses, backend equals quantum computer, will you use any credits on resonance? So don't worry about that. As long as you don't run those jobs, many, many, many times, you won't be using up too many credits. All right. All right. It looks like it's time to get started again. So go if you haven't, let's Stefan or Nadia, could you please put the link in chat again? Because I'm going to change over to sharing my my lab notebook. All right. So today in lab, we are going to be uh, executing two quantum algorithms in CRISP and simulating the results and running them on the quantum computer. So let's get ourselves set up. So as a reminder, you should start out by setting your Python in runtime environment. So I actually don't see the little Python thing at the bottom right here in my screen. So I'm going to set this by going to runtime, change runtime type, and we want to make sure that we're on 2025.07. Please do not use the latest runtime version. Use 2025.07, or things will be a little bit more difficult for you. So your settings should look like this, and save. And as a reminder, we want runtime, change runtime type. If you see the little Python 3 thing down here, you can, in the bottom right corner, you can also do that, but I don't here. All right, so once we've set the runtime environment, we've got to install some packages for Python. So I'm going to do that. Remember to run a cell, we just click the little play button here, and this is going to take a little bit of time. So I'm actually doing this live so that I don't get too far ahead of anybody in this process. Okay, the whole thing doesn't seem to be running at all though right now, so I'm going to refresh and see if that works. Actually, sorry, let me do this as a copy real quick. Okay, because I'm the editor. All right, let me check my runtime, 2025.07, so we're good. All right, and this is why we don't do this live, because I seem to be having similar issues to some of the things that many of you may have been having problems with. Okay, it'll probably just take a little while to run that.
Yeah, it's still connecting to your Python runtime.
Yes, I see.
Top
Up
right
here,
corner.
it's still connecting.
So it disconnected, I think, in the time you were giving the lecture before.
That makes sense. All right, so yeah, I'll let that connect. So we can do a little bit of coding before we run these. We just won't be able to run the code quite yet. Okay, so the first thing we're going to do is we're going to implement the Bernstein-Vazirani algorithm. And you can read through, but this is a summary of what we did in lecture. There are a bunch of different steps. So we start by having our guess or input qubits in the state with all zeros. Then we apply Hadamards, we apply the oracle, we apply more Hadamards, and then we measure. Okay, so we want to perform steps 1 and 2. So we want to initialize our n qubits, where n is the length of the code. So here's our length of secret code happens to be 4 here, but we can change that around if we want. Okay, so can anyone remind me in chat what command we have? Oh, good, we're connected. So sorry, let me just get this running. Okay, good, pip install is running. And then I'll queue that up to run as well. Okay, so can anyone remind me, how do we initialize quantum variables? Good, I see quantum variable in the chat, but what number should we be putting in the parentheses? What does that number represent? Good. So the number of qubits we want goes inside this command here. Now, the way we're actually going to implement this is our extra ancilla qubit, the answer qubit, is going to be implemented separately. So we'll see where that comes in just a little bit. So if we were doing all of the qubits at once, we would indeed want to do 5 qubits here, but we're going to worry about the answer qubit later, so we'll come back to that. So what we're going to do is 4 qubits here. But let's just make this code a little bit more flexible so that we can just change our length of secret code later up here, and then we can reference it again later. So oops. So now I've got the restart session thing, which I'm going to do once. And then if it throws that error for me again, I will cancel it. There we go. Let me just make sure that my packages are all installed properly by running that again. And if the error comes up again, I'll ignore it. Okay. So do we need to do any? So we've set up 4 qubits, which we've called the inputs. Now, my question is, do we need to do anything else in order to turn those qubits into the state we want, which is all zeros? You can answer in chat. This is a quick poll. No, nothing else. So when we initialize qubits in a state like this, then they're automatically in the all zero state. To do means that we have means that you're supposed to fill that in. So that's something that you're doing interactively. Good. So, and the pound signs mean a comment, so it doesn't actually change anything. So the inputs are automatically in the state 0, 0, 0. Okay, so now we're told to apply Hadamard gates to all qubits. So see, I just got this, this restart runtime thing again. I'm just going to cancel it, and it should work just fine. So let's check if my crisp import works. I get a warning, which I can ignore. And that's going to run for a little while, but we should, oops. Oh, dear. And this is, let's see. Let's see if this runs anyways. No, it didn't work.
Interesting, but you can pin the NumPy install in one of the cells if you do.
Yeah. Let's see.
Pip
So
install NumPy and then fix it to version 2.
Install NumPy. Let's
equal
see the syntax for that.
2.0.
Equal 2.0. Yeah. Thanks.
Equal 2.0.
Let's get that running. All right. We'll see if that's working. In the meantime, oh, successfully installed. Let's make sure that yes, this is a very typical day. But this is actually why I wanted to run this live today, so that if we have...
You restarted the session this time.
Yeah, I do actually need to restart the session. But this is why I wanted to run it live, so that you all can see that some of the debugging, and I don't get too far ahead of you, those of you who are debugging. All right, let's see if this is working. Give that a few seconds. Okay, this should be fine. Let's make sure that runs. Yep, okay, we're running. All useful now. Yeah, so if you're running that if you have that NumPy issue, go ahead and where did that line go? Yeah, go ahead and run this line of code, add this line of code in as well. I'll put that in the chat real quick. Okay, so now that we've done that, the second step of our Bernstein-Vazirani algorithm was to perform a Hadamard gate on all of the qubits. So what do we do? What's the syntax for applying Hadamard gate? It's just H. And then if we put H of inputs, what this will do is there are 4 different qubits. And so what this will do is this will automatically apply a Hadamard gate to every qubit in inputs. So it will apply all 4 Hadamard gates that we want. So that's all we need to do. We don't need to do H of inputs 0, H of inputs 1, so on and so forth. Just automatically does it. Okay, so the first 2 steps are just done in 2 simple lines of code. This one and this one. No for loops, nothing like that. Chris makes this super easy. Okay, so the next thing we need to do is implement the oracle. So the idea to be in all possible states. So here's our simulation running, and it says that all possible states have a 6.25% chance of being in that state. All right, so the next thing we need to do is the oracle. So in principle, the oracle has to be handed to you by someone else. Otherwise, this isn't very useful because then you already know the secret code. There's no point in running the oracle. But for practice, we're going to actually try to make the oracle ourselves. So here is where we want our extra qubit. This is where that answer qubit comes into play. Because if you remember last time, we applied C0 gates, or sorry, from lecture. We applied C0 gates or CX gates to the extra answer qubit in order to get us the minus signs that we wanted. So what's supposed to happen is every time that the qubit and the secret code match, in each digit, then we want to flip the answer qubit. So we're going to need to do this for every bit in the secret code. So before we go any further, let's actually define a secret code. So here's a secret code. I just made one up, 1101. But our function should work for any secret code. So what we want to do is we're going to go through each of the digits in the secret code. So in order to go through each of the digits in the secret code, we want to do a for loop. So we want to run in range length of secret code. So what this is going to do is this is going to give us one step for each bit in the secret code. Now, the first thing we want to do is to compare the secret code, the first digit of the secret code to the first digit of the qubit. So, and we want to do something only if they match and only if they're both a 1. So if secret code I, so that's the ith digit of the secret code, is equal to qubits I. So if they match, and qubits I is 1, then we want to do something. Otherwise, we don't want to do anything at all, right? Or sorry. So if actually, let me. I don't need to put that and in there for reasons we'll get to in a second. Sorry about that. So if the secret code matches the qubits, qubits I, right? Then we want to do something. Then we want to flip the answer qubit if the guess qubit is 1, right? That's what we're aiming to do. In order to do that, there's something missing though. We don't have an answer qubit yet. So maybe we should define one. So we're going to define ourselves an answer qubit over here. And how do we initialize ourselves an answer qubit? We need to make a new qubit. And so we're using quantum variable. And we just want one qubit, so we do this. But if you think back to the Bernstein-Vazirani algorithm, we said that we wanted our answer qubit to be in the state 1 at the beginning. We don't want to input 0. We want to input 1. By default, quantum variable always gives us a qubit 0. So we need to do something in order to turn it into state 1, which I'm seeing starting to show up in chat now. We need to apply an X gate of answer qubit. Oops. Helps to use your consistent syntax. Good. So this puts our answer qubit into state 1. But then we also said that at the beginning of the Bernstein-Vazirani algorithm, we also need to apply a Hadamard gate. So we also need to apply the Hadamard to our answer qubit. So we need to start with that to prepare the answer qubit correctly. Good. So now that we actually have our answer qubit to work with, then we should we now need to do this thing where we flip the answer qubit if qubit I or qubits I is 1. So what gate flips a qubit if another qubit is in the state 1? Answers in chat. Excellent.
One quick comment, Danny.
Yes, please.
I think it's totally fine if we check for if the secret code at position I is. We don't need to make the comparison with the qubits I.
Yes, actually, that's true. We don't need that. You're right. Good point. Yeah. So good. Equals 1.
Yeah, equals 1. But...
yeah, that's a good point. So this is the problem with live coding. You're not necessarily very efficient. So if the secret code is 1, then we want to flip the answer qubit if the qubit is also 1. So we heard that the answer is a C0 gate, indeed, which is implemented in CRISP as CX. So we want to flip the answer qubit if qubits I is 1. We want to flip the answer qubit. And that's all we have to do, because that's what a CX gate does. I see HCZH in the chat. That's also correct, but we're going to go with this slightly simpler way. Good. So that makes our oracle. For each digit of the secret code, if it's 1, and also if the answer qubit is 1 in that spot, we flip, sorry, if the input qubit is 1, we flip the answer qubit. And then we send back our qubits. Now all we have to do is call the oracle. So from before, so I'll actually, yeah, so in order to get this running, let me go ahead and do this. So we want to apply our oracle to the input qubits and our secret code. And then we have to apply a final round of Hadamard gates, which is just with our H. We do use CX in CRISP. So CX is not native to the IQM hardware, but CRISP will handle dealing with all of that for you. So you don't have to, we don't need to use CZ. All right, so now let's see what happens if we print the inputs. Sure enough, it spits out our secret code. Now, that's not so amazing because we programmed the Oracle right now with a particular secret code, but you imagine somebody just handed you that Oracle code, it would still work. You wouldn't have to actually know that. We just knew the secret code so that we could make the Oracle ourselves, which is what our friend would do in a more realistic situation. And now we can see our circuit. It looks like this. Now we can run the whole thing on the IQM backend. So that's all automatic here. You just need to get your API token ready. So go ahead and copy your API token from yesterday. Oops, that's not what I wanted to do. Run this cell. It asks about your API token, which I paste in. And let me not show that output. Let this run. There might be, I wonder if there's a queue on Emerald right now. I didn't actually check if Emerald has a queue. Ah, yes, Emerald has a long queue. So let me actually cancel that for myself. I'm going to connect to Garnet instead, because that's going to make life a little bit simpler. And now this should run much more quickly. There we go. And so now we see that indeed the actual quantum computer spits out the secret code correctly 85% of the time. Okay, that's not perfect, but it's pretty clear that that's the output we are supposed to be getting, and the rest of this is just noise. So indeed, the Bernstein-Vazirani algorithm works, and it even works on the actual quantum computer. It correctly spits out the secret code just from calling the Oracle exactly once. All right. So that's what we've got for Bernstein-Vazirani. So make sure that you get that running yourself. Based on the number of jobs on Emerald, I think that we probably have a lot of people running that, which is fantastic. And if your Garnet currently has no queue, so if you want to run your job on Garnet, just go ahead and change this line to Garnet, or perhaps Sirius if you like. Either one is fine, but you should be able to get that running. Excellent. So with that, while you all get yours running on the real quantum computer, let's take a look at the variational quantum algorithm. So here, we're not going to be implementing everything from scratch in the same way. Here, we're going to be using a package that IQM has built called IQM QAOA, which you'll have to install before we get going on here with this line right here.
While it's installing, maybe you can go back again to step 3 and 4 of part 1. I think that was a question asked in chat.
Sure, good. So, sorry, the Oracle or the step 3 and 4 part?
3 and 4 part was explicitly asked.
Right. So step 3 is just we pick ourselves a secret code. You can pick whichever 4-digit secret code you want, and you'll be fine. And in fact, you can make a longer secret code. Let me cancel that. You can make a longer secret code if you'd like. You'll just have to run this cell with the correct length of your secret code. But you make your secret code. And then the idea is that we want to apply the Oracle to the inputs. And we do that, we've defined a function for the Oracle here. And so all we have to do in order to actually apply it to the inputs is to call the function on our actual inputs and on with the secret code that we've defined, like this. So that's all that step 3 is doing. It's taking this oracle we've defined and actually using it on our quantum variable, which we called inputs earlier. And then step 4 is just to apply Hadamard gates to all of the inputs. And H is the syntax for applying a Hadamard gate. And if we just put in our quantum variable, which has 4 different qubits in it, it will apply H to all of them. And if we see the circuit that we've built, it looks like this. So there's 4 H's. Let me annotate real quick. This was our initial step. Our oracle is getting called, let's see, our oracle is getting called in here. And then it's shown it in kind of a funny way, but these are our final Hadamard gates. So that's the same circuit diagram that we had in the lecture, just with the C0 gates for the oracle shown explicitly. So Stefan and Nadia, were there any other questions to address live for the Bernstein-Vazirani part?
Not that I would say directly.
Yeah, me neither.
Sounds good. All right, oops, let me clear my annotations. All right, so now let's go down to the QAOA part. So you may have seen that I got one of those restart your session things. Don't worry about that. Unless you get an error later, you shouldn't have to restart your session. So I'm just going to hide that for now. Okay. So in class, or in lecture, so what we're going to do is we're going to set up our cost function. So the cost function looked like this in lecture. We sum over all of the friendships. I and J are representing students. A number, which is 1 if they're friends, and 0 if not. So we want to ignore anyone who's not friends in the cost function. And Z is -1 if student I is in room 0. And it's +1 if student I is in room 1. We're going to be using some software packages, though, which instead of writing in terms of the Z's, we have to write it in terms of the 0s and 1s, right? So our qubits are in states 0 and 1 rather than state +1 or -1. So we have to, so we can't use this ZI business. And so there's a little bit of math that you can do. You go ahead and check that Z is related to X. So X is 0 or 1. Z is + or -1. So there's a relationship here. So this is actually the cost function we want. It just looks like this. Okay. Now, Jij is 1 if students I and J are friends, and 0 otherwise. So here is our map of friendships. So we need to encode that into the Jij matrix. So let's see how we do that. All right. So for example, the first row, let's decide how we want to encode the students. So let's say Alice is the first student, Bob is the second, Charlie third, Diana fourth, Eve fifth, and Frank sixth, right? So we have to decide that we're going to order the students like that. So now let's look through this J thing. So the first entry here is J11. So we look at the first student, Alice, and ask, is she friends with herself? Well, that doesn't really make a lot of sense. So we can just go ahead and ignore that and call that 0. But now, let's look at the next entry. J12. So we ask, is student 1 friends with student 2? So student 1 is Alice, and student 2 is Bob. And are they friends? Yes, because there's a line that connects them. So what do we need to put into our Jij in that entry? You can go ahead and answer in chat. Yeah, we should put a 1 there because they're friends. Let's look at the next one. We're in J13. So we're looking at Alice, who's first, and Charlie, who's third. Are they friends? Yes. So we put a 1 in there. So now let's look at the next one. J14 we're looking at Alice, who's first, and Diana, who's fourth. Are they friends? There's no line between them, so they're not friends, and so we need to put a 0 there. And in fact, Alice isn't friends with anyone else, so we put zeros in all of those. So that's all we need to do, and we need to do that for each pair of friends. Now, you'll notice that there's a bunch of zeros in there. That's actually done because J12 and J21 are the same two people. So we would actually be double counting all of the friendships. So don't worry about those zeros. They're just there for technical reasons to make sure that we don't double count the friendships. If you wanted to, you could make this matrix symmetric instead of upper triangular, if you care about that, and you'd get the same effective answer. It would just be a little different in how it's implemented, but not a big deal. Good. So I will let you all fill that out. I am going to actually do that as quickly as I can. I will let you all think about that, the rest of those. So you should do that on your own. That's 1, just so that we have something to work with. So then I'm going to run that code. But you should fill in the rest of the Jij matrix yourself. Okay. The next thing that we're going to be doing is creating an object that represents the max cut problem and the cost function. Now, there's this module called DIMOD, which has a bunch of really handy tools for creating these functions. So our next task is to actually put this whole function into the code. So what we're going to do, we've got some utility code here that creates the variables xi. And this quick sum thing is implementing the sum over I and j. So if we look at our cost function, there's a sum over I and j that's being implemented already for you. So you don't have to worry about that. So all we have to implement is this part, the jij 1 minus 2xi, 1 minus 2xj part. So let me see if I can actually copy that function down here. I bet we can't. There we go. So this is our cost function. So conveniently, we already made the Jij matrix. So we just have to reference Jij. And then we're going to multiply that by the other things going on in the cost function. So one of them is 1 minus 2xi, sorry, 2 times xi. But xi is a list of all of the binary variables. So if you notice in the comment here, xi I is it represents the variable xi. So if we put that in there, this is the variable xi. But now we need to do something different. We don't want to take xi times xi. We want to do xi times xj. So for that, we just index xj instead. So this is our list of variables, and we're picking the jth element in here. And the ith element here, this 1 minus 2xi and all of that stuff is just from our directly from our cost function. Oops, and what did I do? Oops, it's called Jij, not J. We named the matrix Jij. There we go. So go ahead and if you weren't able to quite follow along with that, go ahead and think about that a little bit more later. But what I'm going to do now is show you how this cost function gets fed into the QAOA software so you can actually run QAOA automatically yourself. So this stuff, what this does is this creates a problem which can be solved by the QAOA algorithm. There's nothing to do in this cell. I'm just going to explain briefly what the code does. This part, we created a cost function up here called cost. And so all this is doing is it's saying, oops, we're defining that the cost function of this problem is the one we defined in the earlier cell. And then this thing just converts the problem into an instance of the particular problem. So that's for technical use. So we just run that. Okay. So now we need to connect to resonance. This is going to look a little bit different than what we did before, but that's just connecting to resonance is here. And this stuff is making it so that is basically setting it up so that we can tell the QAOA module, which is running the algorithm, to please measure using the quantum computer. It's just the way that we have to tell pass the quantum computer information into the QAOA module. So I'm just going to run this, and it asks for my API token. So I'm going to put that in. Done. It's going to take a little bit to connect. Oh, and this is doing Emerald. So actually, let me stop that. I'm going to do Garnet, since Garnet seems to be running a little more efficiently today. And that finished. Great. Okay, so now that we've done that, the rest of this is going to be running QAOA. So all of that was setting up the problem, and now we just need to run QAOA. So the QAOA algorithm has layers. It applies a particular quantum circuit, which is written like this, but it's some quantum circuit, to the input guess, and it's got two parameters. One parameter is called beta I, and one of them is called gamma I. And so what we need to do is tell QAOA how many layers we want to run on. This is something that you can just play around with and see what you can find. So I'm going to choose to run it on one layer. That seems, with one layer, that seems perfectly fine. Then we also have to tell it initial guesses for these parameters, because what it's going to do is it's going to optimize those parameters. The beta and gamma are just some numbers that we feed into the ansatz, and we want to choose the best possible beta and gamma. And it's going to do that automatically, but we have to put a guess in. So I'm just going to pick a random guess, and maybe beta is going to be 0.1 and gamma is going to be 0.2. I don't know. I'm just making that up. That's perfectly fine. If you play around with this, you may see that the performance is a little bit different. And so now I'm just going to run this, and this line optimizes the parameters. So this runs the optimization loop. It actually does that extremely quickly. Secretly, it's doing a shortcut, but we'll use the quantum computer in just a moment. Okay. Once we've got this all optimized, we have to actually read out. And so what that means is that it's this optimal circuit should turn the input state into the answer to the problem. We just got comment in chat, which was very helpful, that it is actually, the optimization is better if you put in some initial angles. You're not required to do that. Yeah, that's correct. That's an optional parameter, but it does tend to help. Good. So what's going to happen here? Let's run this and see what happens. That's going to run a resonance job, so it's going to take a little bit of time. Okay, so what this did is it spat out a whole bunch of possible states for the qubits and the number of times it measured that state. And it looks like the most probable outcome was 100110. And the cost of that was -12. Okay, so let's actually see if we can understand what that means. So this is saying, remember that this first qubit outcome represents the room that we assigned the first person to, which was Alice. And so what we've got is that Alice, BC, Diana, and Eve are assigned to room 1, and the other 3 people are assigned to room 0. So that's what it told us is the best possible outcome. So let's actually take a look and see if it gave us the right answer or not. So I'm going to switch over to the simulator for the max cut problem. So give me just a moment to do that. There you go. And what it did is it spat out the answer that Alice, Diana, and Eve were in room 1, and Bob, Charlie, and Frank were in room 2. And sure enough, if you remember earlier, there's only one friendship that's in the same room between Bob and Charlie. The rest of the friendships are all broken, and it turns out that that is optimal for this case. So it did give us the right answer. Now, unlike Bernstein-Vazirani, nowhere did we actually have to put in that information. It just spat it out for us. And it told us that we should assign A, D, and E to one room and B, C, and F to the other room. So that's pretty amazing, that it just ran this this quantum optimization algorithm, and the most probable outcome indeed broke up the maximum number of friendships. So that's the power of QAOA. It goes and does that optimization problem for you. It may give you a different most probable outcome in general because somebody is saying that they ran it with Sirius and it gave a different most probable outcome. So that is possible due to quantum noise. So there's a couple of things that happen here. So one of them is there is more than one solution that gives you the lowest possible cost. So for example, I could just go ahead and swap the rooms of all of these people. So that would give the same cost. I'm seeing a couple of other options that come out. So I'm actually curious. Let's take a look. So somebody said that they got 100001. So if your cost function was higher, then that means the QAOA didn't run successfully. Or you might have made a mistake in your JIJ. If your cost function was also -12, then that's different. Then that should also work. So I've been asked to repeat the way that the room numbers are decided from the output. So let me see if I can get both of these things on the same screen. I'm not sure I can. Okay, so I'm going to put into chat an output here. The one that was given to me was 100110. I've just put that one into chat. So we look at the first one, and it says there's a 1 in the first qubit. So that means let me actually reset this real quick. That means we assign person 1, who's Alice, to room 1. So here it's 1 and 2 instead of 0 and 1. But we assign Alice to one of the rooms. Now we look at the second qubit. It spits out 0. So that means we put the second person, Bob, in the other room. The third qubit is 0, so that means we have to put Charlie and Bob in the same room. And then Diana and Eve both got 1, so they go in the same room as Alex and Frank over here. I'll come back to the cost function again a little bit later. If you got a different optimal cost or best cost found by QAOA, double check your cost function. There might be a mistake there. I do want to highlight before a couple of other features, though, of the QAOA module. So here, for example, this line actually classically finds the best possible cost. And it does that by brute force. It just tries all the possible assignments of rooms that you could possibly get. So if I run this, it says optimal cost, -12. If you run the best sample, it's possible that the most probable outcome is not actually the best one. That is possible. So it's sometimes helpful to run some of these other things and check if, so in general, QAOA is going to produce a lot of possible outcomes, but not all possible outcomes. So hopefully one of them will be maximal. Even if it's not the most probable outcome, hopefully it will still produce the best outcome. This says the best sample found by QAOA might be a slightly different one, but it has the same best cost. So that also works. The JIJ matrix does affect the cost. In fact, the JIJ matrix sets the cost. So make sure that your JIJ function is correct in this case. So we're going to leave for a few. So there's some. There's a little bit of other code snippet here to play around with, which will generate random graphs for you. So for example, here, this one is going to generate a random graph that looks like this. So this is, we imagine, our friendship graph. It looks really complicated. And QAOA is going to find that the optimal setup for this graph. There's some, you can adapt the earlier code to run QAOA on this randomly generated graph. I encourage you to play around with it. I just want to mention that you don't have to make the cost function yourself. This random max cut thing actually makes the whole problem for you. So all you have to do is treat random max cut the same way that you were treating this max cut instance earlier. So anything you ran on max cut instance, you can run with this random max cut problem. I encourage you to play around with that on your own time. And then there's a homework assignment, which is implementing another quantum algorithm on your own time. Please read up on Grover's algorithm. It's another classic algorithm, which we just don't have enough time to get into today. So with that, I'm going to wrap up for the day, and we'll stick around until about 1 o'clock Munich time. So that's another 20 minutes or so to answer questions. So thank you all very much for attending, and I hope you were able to get some code running and on the quantum computer and had everything and found this informative and enjoyable today.